We have been discussing the ohmic contact in our last lecture, and at the towards the end we touched upon some aspects. One is about the interface state density distribution, why it is distributed across the band gap, we discussed, and then we also discussed why all those donor levels are towards the valence band side in the band gap, and all the acceptor side levels are towards the conduction band. In the sense, they are located above the donor level. This we have illustrated with an example from gold in silicon, because it can be gold can be donor or acceptor, and there those deep donors are 0.3 electron volts above the valence band, and deep acceptors are mid gap. So, with that we understood, and we also began some discussion on the effect of interface state density on a free surface. In the sense, no metal put, what will happen? That is what we started on. I have drawn the energy band diagram here. So, today we will discuss first A part on that, then we will go on in the B part on the IV characteristics of Schottky barrier diodes. Okay, because this particular aspect what we discuss A is very important for field effect transistors in gallium arsenide, because you can have devices which are not working due to these effects. Okay, now let us take a look at this. This diagram illustrates the conduction band, valence band, Fermi level, that is N type material, and we have the DIT distributed all through the surface here. I just put this E naught here. Above E naught, whatever levels are there above E naught, they are all acceptors. Now, once the Fermi level is in this position, all the levels below the Fermi level will be occupied. I have just marked with color the region between EF and E naught, just to tell you that those are the acceptor levels which have been occupied by electrons. When acceptor level is occupied by electrons, the charge is negative. The levels below E naught, okay, levels below E naught, they are also occupied with electrons, but they are donors. Donor level when it is occupied, the charge is 0, it is neutral. So, we have to consider that this region between EF and E naught, okay, acceptor states below EF and above E naught are occupied by electrons. They are negatively charged as a result of occupation of electrons. Correspondingly, so once there is negative charge in the surface, it has come from somewhere. It has come from the bulk of the semiconductor, and in the bulk it can come from the very corresponding very close to that point, just near the surface, below the surface. If you look at the top of the surface, that is below the surface. So, those charges have come from there. If those electrons have come from there, it leaves behind positive charges. What you mean by that is, just below the surface there is a positively charged layer, in the sense there is a depletion layer. Okay. The N type material, when it is depleted, it has positive charge. It is depleted because those electrons have gone and occupied the surface states here. Okay. So, I have marked the total charge here will be QIT. So, this particular diagram what I have drawn is actually the beginning. Just the moment this is charged with electrons, there will be depletion layer, and the depletion layer charge will be equal to whatever charge in the space charge layer. So, that correct diagram I have drawn next. You can see, if it is like this, if I draw it like this, energy band diagrams are flat, which would mean there is no depletion layer. But the very fact that there is depletion layer, energy band diagrams will bend, and it will be like this regular Schottky barrier diode. You do not have metal there. Without the metal, you have got now a depletion layer formed here up to this point. This red portion here is the depletion layer, this is the surface state charge QIT, and this is the neutral region. Notice one thing, when this has, I will go back to the original diagram, here entire charge was here, but as it starts bending down, Okay. This point comes down, along with that the Fermi level in that portion comes down. So, what happens is, as the Fermi level comes down, the occupancy here goes down, because levels below E f and E naught are occupied. When the depletion starts building, the Fermi level comes down and less number of charges are occupied. So, this process takes place till there is equilibrium between the charge in the interface and depletion layer. So, till that time that band bending goes on taking place, like the electrons are transferred from the semiconductor to metal or metal to semiconductor. Here the electrons are transferred from this bulk into the surface, till the charge here QIT is exactly equal to the charge here, and charge in the depletion layer is equal to per centimeter square. Of course, we are putting Q into Nd is the donor concentration into the depletion layer width, Wd is the width of the depletion layer, okay, and that is positive, and that positive charge is exactly equal to negative charge within this portion. That is that region which is having QAT. Now, QAT is actually equal to E f minus E naught into QDIT. QDIT is number of states per centimeter square per electron volt. So, we are still keeping it number of states per centimeter square, multiply by the E f minus E naught, E f minus E naught, you get that. This is exactly similar to what you did in the case of Schottky barrier. All that has happened is equilibrium has takes place till the charge here is equal to charge here. Okay. Now, you can see for a given doping concentration what will happen. Here, as this DIT goes up, if the DIT goes up for a given Q and D WD, E f minus E naught will become. See, as Q DIT goes up, if I am keeping this constant, it is not a constant, slightly varying. So, if this is constant, I am just giving as an example, if this is constant, that is Q and D WD, if that is constant, when DIT is large, if it is more in the surface, E f minus E naught will actually be smaller. That means, actually higher DIT values, the Fermi level gets closer and closer to E naught, because a smaller amount of gap between the two is sufficient to supply those charges. E f minus E naught into DIT. If DIT is large, this gap need not be large. So, when DIT tends to closer and closer to infinity, which is not realistic, but when it becomes very large, E f becomes almost matches with the E naught. That is called what is known as Fermi level pinning. Fermi level tends to pin to the E naught level. It will not pin exactly, but it will go as close as possible to that, so that a small amount of gap there between E f and E naught supplies enough amount of negative charges to the depletion layer. So, you can work it out, that it will be a nice exercise for you to see what will be the potential. See, I have marked it here as Q phi, I have not called it as Q bi. Bi is built in potential, this also is built in potential, but when you talk of free surface, you talk of surface potential. The surface potential is potential here with respect to the bulk, which is same as the VBI. So, instead of calling it as built-in potential, people call it as surface potential, the potential drop across the depletion layer actually. Okay. Now, let us see, go back to this next diagram. Okay. So, I just few things see. So, phi is the surface potential, that is what I marked here, that phi, and this is phi naught is the gap between the neutral level E naught and E b. Okay. Now, let us take a look at further. I am rewriting that. I am writing only the magnitudes now. I left out the minus sign. Magnitude of charge in the interface state Q dit into E f minus E naught is equal to Q n d into W naught, WD. What is WD? WD is depletion layer width, and that is decided by how much is the potential drop. So, usual law phi is equal to Q n d W square divided by twice epsilon epsilon 0, very well known formula for depletion approximation. WD is that. Now, you can see the whole thing has hit an equilibrium. that locational Fermi level has taken such that E f minus E naught is equal to that quantity, and that quantity is decided by the potential. Okay. So, you can now see substitute, I have not written that deliberately, so you can take it, work out and see W d when I substitute from this, what you get is, all that you get is root of q n d twice epsilon r epsilon 0 into phi. Okay. So, on the right hand side you will have a constant into root of phi, and within the constant you have got n d. Okay. So, for a given n d you have got a phi there. What do you have on the left hand side? Left hand side has got E f minus E naught. E f has changed its position such that square root of substituting this square root of q n d twice epsilon r epsilon 0 phi on the right hand side is equal to that quantity E f minus E naught. Can you write E f minus E naught in terms of phi? But I would like you can actually sit back and work out this. What is E f minus E naught? In terms of phi we want, because ultimately the phi has built up such that E f minus E naught has taken the proper value. So, you write E f minus E naught in terms of phi. How do you write that? I have not deliberately written this here, so that you can have some exercise to do with yourself. So, this quantity now here is the band gap E g, okay, minus phi naught. So, band gap E g minus phi naught, it leaves you with this total this thing plus this E f minus E naught. So, band gap E g minus phi naught minus this total quantity, that is actually equal to q phi and q phi plus E c minus E f. So, all that you have to do is on the left hand side E f minus E naught, you can write from this total width you subtract whatever is above, which is q f plus E c minus E f, and also this phi naught. So, what you get, what I am trying to point out is you get an equation, transcendental equation on the left hand side E f minus E naught expressed in terms of phi, on the right hand side this quantity also is expressed in terms of n d and phi. Okay. So, the moment you fix up n d and the moment you fix up d I t, you can find out what is phi is by solving that equation. I think I would urge that you look into it as an exercise, because that is simple matter to see. Okay. So, all that I am trying to point out from this particular analysis is, okay, ultimately the E f tends to become closer and closer to E naught if d I t is large. Okay. What is the maximum value of phi that you can get? Go back to that diagram. What is the maximum value of phi that you can get? d I t tending to infinity. Okay, you can see, and this and d I t tends to infinity, E f gets pinned on to E naught. So, what you get will be actually equal to E g minus phi naught is that quantity, E g minus phi naught minus E c minus E f. Okay. The maximum value is when this merges with that. So, this gap goes off. Okay. So, this phi will be equal to E g minus phi naught minus that quantity. Okay. You can figure it out very easily. It is just what you have to take a look into the thing. So, that is what I am trying to point out is, whatever be the d I t, your phi will never become equal to band gap. It will be 2/3 of E g by q. That is what I am trying to point out. So, in an example where the d I t is infinite or very large, the potential there you can easily immediately know. The potential there is actually 2/3 of E g by q minus this quantity E c minus E f. If E f merges with E c, straight away phi is equal to 2/3 of E g by q potential. Okay. And once you know phi, you can actually find out what is the depletion layer width is, because phi is q n d w d squared by twice epsilon r epsilon 0, standard formula. Okay, with that I think I will leave this topic of Fermi level pinning or the effect of interface state density on the barrier height in Schottky, and also on the free surface. Please remember that a free surface with high interface state density can lead to a depleted surface below, which has profound influence on the MOSFET. Okay, when you go to that, we will see. Between the gate and the source, there can be a depleted layer due to free surface. Just let me put that down, so that without leaving you on guessing. For example, if I have a semi insulating gallium arsenide, okay. So, all our effort was to realize a MOSFET, okay. And then I have a N type layer gallium arsenide, and here what we do is you will put a Schottky barrier, that is the metal gate. Okay. Now, you will have ohmic contacts on two sides, which will make N plus and metal. So, you will have a contact here like this. Notice I am putting it buried inside, because you have alloyed N plus into that, and on that you have got the metal. So, that is the source. Similarly, I have got here drain, and this is the gate. This is the free surface that we are talking of. In the example that we have considered, we had first discussed Schottky barrier, metal semiconductor contact. We saw the impact of the interface state density on the barrier height. Okay. We will see how the barrier height affects the current or the blocking capability soon. Qualitatively we have discussed, we will have quantitative discussion now. This we have discussed, make it N plus to make ohmic contact. Here, this free surface, what will be the effect of that? This is N type free surface. If you allow without any passivation, if there are infinite number of dangling bonds, you will have depleted layer below that. If you have depleted layer below that, you can immediately see the difficulty. What is the difficulty? Supposing this depleted layer comes all through like this, what happens? Source is disconnected from the channel. That is the problem that we will face in the MOSFET. This is one of the difficulties that people are facing when making this type of device, particularly if this layer becomes thinner and thinner, because after all, as we said, the potential here is equal to 2/3 of Eg at the most. Correspondingly, how much is the depletion layer depends upon the doping here. So, if I have a thickness only that much, maybe you can say there is still some opening path is there, it will lead to increase in resistance. But if the thickness is this much thin of this layer, entire layer is depleted. There is no path between source and the channel. So, the MOSFET will not work. It is like just like the MOSFET without an inversion layer connecting the source and the channel. This is why, okay, depleted layer. I will just remove that from there, let me put it somewhere else. Okay. This is the depleted layer. Due to DIT. That is all what I want to point out right now. Now, we will get back to our discussion on the Schottky barrier. As I have shown in the first slide itself, what we now do is take a look at the conduction mechanisms or the IV characteristics of Schottky barrier diodes. This is the metal and this is the semiconductor on this side. As I pointed out earlier, we will be discussing only N type substrate, because we are interested in electron transport. So, here this is the N type semiconductor, and conduction band Cb, valence band Vb, all these abbreviated because later on we will say Cb and Vb, and semiconductor Sc. These are abbreviations I am following to make it easy to project it here. So, in the Schottky junctions, people call it also Schottky barrier, metal semiconductor contact, at the Schottky barrier or even Schottky junction with the metal, with the semiconductor. You can see here these circles are the electrons, these open circles are the holes in the valence band. Now, the current transport, there are different mechanisms by which electrons can be transported from the semiconductor to the metal. From the metal, it can be transported if the electrons have energy above that. That we have already discussed, that is called thermionic emission. Okay. Thermionic emission means if you heat up or at room temperature, several electrons will have energy over and above this barrier. If you look into the old vacuum tubes, I do not know whether I told you the example, if you take the vacuum tube, what is the source of electron there? It is a heated filament. A filament is heated, sufficiently heated, red hot, so that it emits electrons. Okay. If you take a metal, okay, if you take a metal and then if it is in vacuum, there is a barrier that is 0 level, and what as we have said, that is phi m. If I heat at room temperature, if you take a metal, electrons are not coming out of that, electrons are staying within that because they have the energy like this. But if I have barrier here, like in the case of Schottky barrier, these can cross. If I do not have anything, only vacuum, these electron energies have to be raised up to that. If it is raised up to that, but if I heat up the metal, it is not the Schottky barrier that I am talking of, in the vacuum tube actually, you heat up the filament, these entire distribution will become like this, acquire kinetic energy, they can be emitted into the space. So, in vacuum tube what they do is, you have evacuated tube in which there are 2 electrodes and just close by to the cathode you have this filament is heated. So, now apply voltage, the electrons which are emitted, okay, can be corrected by the plus. So, you have the current flow. That is the way the vacuum tube works. Okay, it is just in case we do not have a chance to talk of vacuum tube these days, though that was the main device in olden days. So, that is the transport of electrons from here to here. From semiconductor there are different mechanisms. One that we have been talking of, transport of electrons across the barrier. Okay, just I have written that down here, that is the thermionic emission. The A that I am putting here, okay, that A is the transport of carriers across the barrier. Okay. Transport of electrons from the conduction band Cb of the semiconductor over the top of the barrier into the metal, that is called thermionic emission. That mechanism that we are talking about, whichever has got energy above the barrier can cross. Second one, hole injection into the neutral region of semiconductor, that is this one, B. Holes injected from here, whatever vacancies are there will be injected, they will be transported into the neutral region, and you can see it is beyond the depletion layer, and in the neutral region it will recombine with the electron. This is the recombination process. It is just like in the case of p-n junction, in a forward bias. In fact, I have shown here the forward bias device. Okay, it is not thermal equilibrium. So, in a p-n junction, when you forward bias, you have hole injection from p to n. Similarly, your hole injection, whatever vacancies are there here, they are injected into the neutral region, they will recombine. Okay. We have been very silent about it so far. We have been talking of only this transport. I have been silent because you will see later on that that particular component is very small. Okay. Another component that is present, which is negligible in many situations, most of the situations, is generation recombination. See, notice here electrons reaching the depletion layer, holes reaching the depletion layer, recombination. Okay, in the forward bias case it will be recombination. If it is a reverse bias case, what will be the situation? Electrons will be lifted up from the valence band to conduction band and separated out, that is generation. So, that is why the C component C is recombination or generation. Recombination in forward bias case, generation in the reverse bias case of electrons and holes in the depletion layer. So, B and C what we have discussed just now, both are same. Ultimately, it is if it is forward bias case, the part B, go back to the diagram. Here the recombination is taking place in the neutral region. Here C, recombination taking place in the depletion region. The reverse bias case, this is absent, this will be generation current, opposite. There is one more component here you see, which actually is very close to this top edge, electrons which are having energy not above the top of the barrier, but very close to the barrier edge. Okay. Those electrons find the width of that barrier small. As you go from bottom to top, I will just draw that because it is not very clear effectively there. Suppose I have a diagram like this, and if I have this Schottky barrier like this, I am just showing it now. Let me draw slightly differently. It is not a light heavily domed stuff. Barrier is wide here, maybe 200 angstroms, 300 angstroms, or even 0.1 micron. But when you go to the top, what we are talking of thermionic emission is the injection of electrons across that barrier A. What we are talking of is the electrons which have energy here. They find that the barrier width is very small. Okay. That is quantum mechanical tunneling, that is called. Okay. I think the physics people frighten us by using jargon term, but it is actually the fact. Schrodinger equation solution tells you all the things. So, what I am trying to point out is you will have very easy transfer of electrons from here to here across this thin layer, that is called tunneling. In fact, you can call quantum mechanical tunneling. In fact, tunneling is a simple term. The idea is when the layer is very thin, the probability in terms of quantum mechanics, the implication is if I have a thin layer, the probability of finding the electron here and here are the same, because it is wave function of this electron, because this electron is a particle and also a wave. The wave function overlaps onto the other side. That is why you can easily, it can be here or here, and if slight amount of force is there, it will find itself on the other side. That is the quantum mechanical tunneling, a very simple term. Okay. So, probability of finding electron here and here are same in the sense it can easily move on to that side, okay, because of the wave function spreading into just neighborhood of wherever the electron is. So, to put it in further simple terms, this it looks as if there is no barrier here, that is called tunneling. Sometimes it is also called as the top one is thermionic emission, this one is called thermionic field emission, TFE, because these electrons have enough energy because of thermal energy here, and this is because of field, the slightest field it will push it across that, because it can easily occupy the other portion because its wave function goes on to the other side also. So, thermionic field emission, that is another name given to that. Okay. So, you will hear terms like thermionic emission, thermionic field emission, these are slightly different mechanisms. Okay. Right now, what we will see is among all these three components, B, C, D, they are not contributing much. The main contribution to the current will be from here. I just included these terms just for the sake of completeness, and also they will show up under certain conditions. If the conditions are favorable, they will show up. For example, you have already seen if the doping is high, that component becomes very high. If the doping is high, then the entire layer becomes thin, like that. Tunneling becomes very easy. Okay. So, that is an example of telling when the when you provide a proper condition, other terms will also start beginning to show up. Otherwise, normally for wide band gap semiconductors like gallium arsenide, silicon carbide, gallium nitride, etc., and even silicon, the main component is A. So, all that we have to see is, if I want to find out the IV characteristics. So, let us see that. So, D is the quantum mechanical tunneling through the barrier, that is that D. So, let me go through one. Thermionic emission, generation recombination current, hole recombination in the neutral region, and that one is a quantum mechanical tunneling. Among all the three, all the four, these are not very important, and when they are absent, when this thermionic emission only is present, it shows ideal characteristics. Okay? Most of the time you get close to ideal characteristics. So, that is what I said just now, mostly determined by the IV characteristics of the Schottky barrier diode is mostly determined by thermionic emission, that is A, process A that we have said. Process B, C, D are generally insignificant. And I say generally insignificant, they are generally within quote. That is, if you bring in, provide certain circumstances, which we will have occasion to see later. One of them I already pointed out, if the barrier becomes very thin, you will have tunneling. Such junctions show ideal characteristics, I is equal to I naught e to the power V by V t minus 1. Okay? Now, let us see a very quick analysis of this. We back to that diagram, which we have been seeing often. Metal, depletion layer, N type, forward biased. So, this line is EC under thermal equilibrium conditions, that is what I have shown here. EF is there. When you forward bias, this goes up, dotted line, and the Fermi level you can call it as the quasi Fermi level EFN, that also goes up. Telling you that you can apply for finding out the carrier concentration, total carrier concentration here, you can use thermal equilibrium situation, and that will be practically equal to the dopant concentration. The entire area under this curve there gives you total concentration N 0, which is virtually equal to ionized dopants. When you forward bias it, this is lifted up, and this particular region where I have marked shaded there, this region, okay, that region is having energy above that barrier. All these electrons have energy above that barrier. Before thermal equilibrium, that was whole thing was down, okay, and now more number of electrons have the energy more than, I am repeating some of the things of course, but just to get into the write down equations, that is the one. If we have to find out how many electrons are able to cross the barrier, what we have to do is find out what are these quantities. You can see that is less than the total area under the curve. So, it is less than the thermal equilibrium electron concentration. Over here, this region, this shaded portion there, those are the electrons which can cross the barrier, which can give rise to current JMS in this direction due to electron injection from here to here, JMS from, okay, that is this one. So, whenever forward bias or reverse bias, this quantity is not changing because this phi Bn is not changing. All that happens is here. So, this will give rise to JMS, which is J naught, usually we call it, whereas JSM is due to these electrons. How do you compute the current? It is different from the way you compute the current in a PN junction. That is the real difference between the two. Why it is, we will see also. Now, let us see. So, all that you do is, supposing I can find out how many electrons are there above this barrier. That is, if I take move from here to here, how many electrons are there here? They are the ones which are having energy above that. As I move from the bulk to this surface, what happens to electron concentration? Keeps on falling, and the electron concentration here, total concentration here is equal to the one which is above that. So, if there are electron concentration N s at the surface, if they have a velocity component V x in this direction, okay, due to their kinetic energy, they are above the valence band. So, due to their kinetic energy, that is due to the temperature, they have got certain velocity V x. Supposing n is the concentration, V is the velocity, what is the current? N into V into Q, as simple as that. So, all that you have to find out, if I want to find out this JMS, that is the current due to the electrons injected from the semiconductor to the metal, all that I have to find out is what is that electron concentration on surface and multiplied by the velocity. Okay? The simple Ohm's law that we usually use, or simple law that we use, not merely Ohm's law. So, this is all that I have said now. JMS is current component due to electrons crossing from the metal to semiconductor. JSM is a current component due to electrons crossing from the semiconductor to the metal. Reverse bias condition, total current is actually equal to, go back, reverse bias condition, the whole thing will be depressed down. So, none of these carriers will have energy to cross. We have discussed this earlier. So, only these electrons will have the energy to cross, that is JMS. See, please remember, JMS is in that direction due to injection of electrons from here to here, metal to semiconductor. So, JMS is actually equal to J naught. So, reverse bias condition, you will have current due to the excess electrons which have energy from the metal to semiconductor, that is J naught. Forward bias condition, the JMS remains same thing, that is J naught. J is actually J naught, which is flowing from semiconductor to metal due to transport of electrons from metal to semiconductor, and JMS is due to, I think this other way, I think this is a mistake here. Okay, just yeah, this actually is JSM minus J naught. Okay, is that right? So, that is JSM minus J naught, because JMS is the one that is changing. So, what we have to find out, if I have to find out the forward bias condition current is, find out JSM. Make V equal to 0 in the expression, what will I get? J naught. So, I do not have to compute J naught separately. Find out JSM as a function of forward bias voltage, find its value when V equal to 0, that gives me J naught. Okay. So, that is the thing, JSM equal to JMS equal to J naught at thermal equilibrium. That is calculated there. I can quickly run through this now, because all the formulae are known to you. Only formula that you do not know is, or you were not applying, is JSM, current due to the electrons injected from the semiconductor to the metal, is number of electrons or electron density near the surface at x equal to 0. Let me go back once. X equal to 0 is on the surface, metal semiconductor junction at x equal to 0. What is the electron concentration there? Okay, multiplied by the velocity that we are computing, multiplied by the velocity component, that is V x bar is actually the mean velocity component in x direction. That is a standard formula for any gas particle from the statistics that comes up. Ns is the electron concentration, is that per centimeter cubed, okay, the per centimeter cubed number. Again one more error there, I will just correct it right here. I think it is a bit difficult. Just give me a minute, I will just correct it so that that is actually the quantity. Okay, Ns per centimeter cubed. So, it is better to, okay, because these are all per centimeter cubed, how much is the thing. So, add the very close to that surface in the bulk, the carrier concentration is that much. Having energy higher than the barrier height on the semiconductor side. Is it okay? Oh. So that is what we are trying to see here. Current is Ns Vx and Nx is per centimeter cube, okay, density, having energy higher than the barrier height on the n side. And what is the barrier height here? When I apply voltage V, thermal equilibrium, it is VBI. When I forward bias, it is VBI minus V. Supposing that is the barrier height, potential difference, what is the Ns? This is the N0 is the carrier concentration in the bulk. From the bulk to the surface, if there is a potential difference phi, the carrier concentration surface will be whatever here is present on the bulk multiplied by e to the power of phi by Bt, q phi by Kt, okay, that is phi by Bt. This is the Boltzmann approximation. Carrier concentrations vary as exponentially as the potential divided by Bt. Okay, that is a well known law. So, I have just used that. So, phi, what is phi? Phi is that quantity minus q VBI minus V by Kt. I am using minus V minus because the potential, go back from here to here when I go, you have potential drop negative. So, if the carrier concentration is Nn0 here, the potential carrier concentration here is equal to Nn0 into e to the power of minus q V minus VBI minus V by Kt, because the potential difference is VBI minus V here. That is what we have done. Very simple actually, and once you have written this equation, if you accept that, in fact, because it is a law, Boltzmann's law, which we have used, carrier concentration between 2 points can be related by ratio of the carrier concentration is e to the power of phi by Bt. That is what I used. So, ratio of the carrier concentration here and at the bulk is equal to e to the power of that. You have to use the sign properly. As you go towards the negative potential, the electron concentration is low. So, that tells you that there should be minus. Even if you do not understand more than that, that is clear enough. So, now what is Nn0? Thermal equilibrium carrier concentration. Okay? That is related to Ec minus Ef and density of states at the conduction band. This again is a standard formula in semiconductors. Nn0 thermal equilibrium value equal to Nc e to the power of minus Ec minus Ef by Kt. So, what I do is I substitute for from 3 into that, and then Ns becomes equal to that quantity. I have rewritten this. Instead of Nn0, I put Nc e to the power of minus Ec minus Ef, and this I put within that bracket, that becomes plus QVBI because minus is there, and this becomes minus minus plus. So, what is this quantity now? If you take a look at this quantity, Vc minus Cf plus QVBI. Okay, let me just put that diagram. Okay, thermal equilibrium situation if you take, this is thermal equilibrium situation, okay, and this is Ec and this is Ef, okay, thermal equilibrium. What is this quantity? QVBI. And what is QVBI plus Ec minus Ef? Bn. That is what you have done. So, what we have done is we have substituted for QVBI plus Ec minus Ef is equal to phi Bn. This is in electron volts, this is electron volts, this also is in electron volts, VBI in volts. Okay. So, we have written that. Now, so that is what we have done. I have taken this out, all these three quantities together, put it as phi b n. So, e to the power minus phi b n by k t, and this minus and this minus together I become e to the power of v by p t. Now, you can see the whole thing has become simple. The carrier con, these are the electrons which are capable of crossing the barrier. So, they are present at the boundary there, and they will be hitting the boundary at a velocity, hitting, okay, impinging on the surface with a velocity v of x in that component. So, current now is equal to q into v, okay. I just multiplied by q into v of x, and this quantity, current is this quantity multiplied by v of x into q. That is what I have written there. Now, what you do is you have to just see, substitute for N c, substitute for v of x, you get the equation for the current. N c is this quantity. Effective density of states is related to temperature and effective mass, twice 2 pi m n star k t by h square to the power 3 by 2. V of x is the mean velocity component from the assembly of particles statistics, and from the energy considerations people have arrived at the mean velocity component in that direction as proportional to root k t. Okay. So, that is the quantity. So, I substitute this quantity and this quantity onto these two. Okay. Root k t by 2 pi m n star is mean velocity component. Substitute that, you get that. That is all put together 4 pi m n star q k square t square by h cube e to the power of minus phi b n by k t e to the power v by v t. Now, the whole thing inside that is J naught. Okay. So, now you see you have got the very famous equation J naught e to the power v by v t. The whole effort has been to find out what is this J naught quantitatively. You can see that. Okay, now, let me just go one step further here. So, that is J m. So, if I put v equals 0, what do I get? That is J S m at v equals 0 is thermal equilibrium value. That is exactly balanced by J m s. So, that is, okay, J m s is same J naught, because otherwise in thermal equilibrium v equals 0 and J S m is J naught, and J m s what comes from metal semiconductor must be balanced by that. So, total current is actually J S m minus J m s. So, I have just subtracted J naught from here, because one is in that direction, other in the other direction. So, this is a diode equation where J naught is given by this expression. Let us take a look at that. So, the J naught is this quantity, whatever I have said just now. Now, this is further simplified to make life easy for us. You do not have to remember that big formula. The entire thing here, leaving the T, that is a constant independent of temperature, you call it as A star. A star is actually Richardson constant, the person who called it by the name A star, Richardson constant. The idea is this A star, you could have used it as a constant, but you can see that there is M n star coming. That means A star depends upon the semiconductor. For silicon it will be higher, because M n star is higher. For gallium arsenide it will be lower, because M n star is smaller. So, okay, into T squared into that quantity. So, you can see that J naught depends upon barrier height and temperature plus this constant. So, let us now go further down, because you do not have to remember even this, what are these quantities. A star is actually this quantity 4 pi m n star q k square by h cube. What I do is, you do not like to have that m n star there. You know always m n star by m naught, okay, because we know for gallium arsenide it is 0.067 or so. So, that is why we multiply this by m naught, divide by m naught. So, you get a constant independent of the semiconductor multiplied by m star by m naught, and this quantity turns out to be 120. I think if you remember that, that is sufficient. A star is 120 into m star by m naught, ampere per centimeter square per k square, degree Kelvin. Okay. Now, you can compute A star. So, coming back to this, so therefore, J naught is A star T squared e to the power minus 5 Vn by kT. So, this is the one which decides what is the voltage drop across the device. A star is 120 m star by m naught, we have just now derived in that quantity. For gallium arsenide, we are estimating now evaluation of J naught. How much is J naught in gallium arsenide? This quantity is m star by m naught is 0.067. A star turns out to be 8.04. So, once you put that as 8.04 A star, T at room temperature 300 degree Kelvin, 300 square, when you do that, you get 9 into 10 to the power of 4 into e to the power minus 5 Bn kT. I take 5 Bn as 0.85 electron volts, close to that EF merging with E naught. So, that is that. You get 1.24 into 10 to the power of minus 9 ampere per centimeter square. Okay. Let us see, just remember this number, it is about 10 to the power minus 9 amperes per centimeter square. Silicon, if you take m star by m naught is 0.6, gallium arsenide it was 0.067, this is not, it is very close to 1. Okay. So, A star is 72. What was it in gallium arsenide? 8.04, 8.04. Here it is 72. Now, let us see 5 Bm, 2/3 of Vg will take. You can't have better than that. So, it is about 0.75. So, then J naught is for this case is 72 is A star, T squared is this quantity, and e to the power of this quantity is 6 into 10 to the power minus 7. Now, what do you say now? J naught in gallium arsenide was 10 to the power minus 9 because of better 5 Bn, 1. Number 2, A star is smaller. It is A star T squared e to the power minus 5 Bn by Vt. A star is smaller, so J naught is smaller. So, mainly because of the smaller effective mass. So, you get that. So, comparison of characteristics of gallium arsenide silicon Schottky diodes, if you do. Okay. We have just now found out J naught is 10 to the power minus 9 in gallium arsenide, silicon it is 10 to the power minus 7. Now, J naught is this quantity. Supposing I take J equal to 1 ampere per centimeter square, corresponding voltage across the junction will be Vt ln J by J naught. So, J is 1 ampere, J naught is that quantity. For gallium arsenide it is 0.53 volts, 513 volts. For silicon it will be, for silicon J naught is higher, therefore, V will be smaller, 0.358. So, what you are telling is, when you take a silicon Schottky barrier and gallium arsenide Schottky barrier diode, the voltage drop across the gallium arsenide Schottky barrier diode for a given current will be larger. In this example of 1 ampere per centimeter square, it was 0.513, in this case it is 0.358. So, to sum up here, comparison of gallium arsenide Schottky and silicon Schottky, 5 Bn is 0.85, 0.75, that itself increases this current. A star is 8.04 and 72, and J naught minus 9, minus 7, forward voltage drop at 1 ampere is that quantity. Okay. So, as a result, you will get, I will just go one step ahead, only compare these two. These two curves are the IV characteristics of the Schottky barrier. Okay. Schottky barrier blue, that is gallium arsenide, about 0.5 volts for a current of 1 ampere per centimeter square, and silicon, the forward voltage drop is smaller. Corresponding reverse currents I have shown here. Gallium arsenide reverse current is smaller compared to silicon Schottky. So, these two, we will do the comparisons between the PN junction of gallium arsenide with metal semiconductor contact of gallium arsenide and p-n junction of silicon, metal semiconductor contact in silicon. Those things we will compare in the next discussion, because now right now we have a good idea about the Schottky barrier in gallium arsenide. Use a cut-in voltage of about 0.53 volt, 0.5 volts, which is close to the cut-in voltage of silicon p-n junction. So, it is almost like that. If I take a semiconductor which is larger band gap, you will get even larger forward voltage drop. Okay. So, with metal semiconductor contact itself, we can get quite close performance as good as p-n junction. So, with that I think I will close down today. We will continue on this discussion, some aspects of this and the non-idealities etc. in the next lecture.